we have to define a capacitor and explain how it functions, explain the charge and the discharging, the charging and the discharging process of a capacitor. We have to calculate the electric energy stored in a capacitor, and finally we are going to determine the equivalent capacitance of a capacitor. First of all, the definition of a capacitor. A capacitor, or sometimes called condenser, is composed of two conductors placed near one another and separated by an insulating material. That is any two metals. Suppose this is a metal and this is another metal, and here we have an insulating material. This setup is called a capacitor, simply. Okay, this is a capacitor, a very simple capacitor. This is the symbol of a capacitor, and we denote the capacitance of a capacitor by the letter C. The capacitance of a capacitor and is measured in farad. We measure it in farad. The capacitance of a parallel plate capacitor. This is the equation of the capacitance of a parallel plate capacitor, not any capacitor. By parallel plate capacitor, I mean the metal will be a plate, and another metal will be another plate parallel to the first one, and here we have an insulating material, as I have said before. This is called a parallel plate capacitor because the plates are parallel to each other. The capacitance of this capacitor equals epsilon node times S over D. I'm sorry, not epsilon node, epsilon. Epsilon node is for a specific capacitance. I will speak about it later. It's epsilon S times D. So C equals epsilon S over D. By epsilon, I means the permittivity of this dielectric material, which is a physical constant that depends on the insulating material. So epsilon is called the permittivity. The permittivity of the insulating material. S is the common area between the plates. That is, if we bring the plates to touch each other, the common area between them is S, which is a meter squared for sure, and D is the distance between the plates. So if we have the value of epsilon, if we have the value of the common area S and D, therefore we can calculate the capacitance of the capacitor. We call it C, and as I have said before, we measure it in farad. Another equation which is very important in this chapter is this one: Q equals C times V. Q is the quantity of charge accumulated on one plate of the capacitor, or on the positive plate of the capacitor, and V is the voltage difference between the two plates. The relation that relates the capacitance of the capacitor with the voltage across its terminals and its capacitance and its quantity of charge, is Q equals C times V. Okay. Consider a parallel plate capacitor. Here we have the capacitor. Here we have the voltage source. Here we have the voltage source, the battery. Here we have the parallel plates of the capacitor. Okay. At the very beginning, when the voltage of the generator is 0 volts, the quantity of charge on each plate is 0. And the capacitor in this case is called a discharged or empty capacitor simply. Or uncharged capacitor. This is an uncharged capacitor. What happens if we increase the voltage of the DC generator? Look what happens. Whenever I increase the voltage, therefore this plate acquires a positive charge, and this plate acquires an equal, in absolute value, an equal negative charge. Why the positive charge here and the negative charge here are equal in magnitudes but opposite in signs for sure? Okay, the metallic plate here initially is neutral. By neutral I mean there is no excess positive or excess negative charge on it. This is at the very beginning. So in this plate, the same number of positive charge, the number of positive charge is the same as the number of negative charge. Once this plate is connected to the positive terminal, the positive terminal will attract some of the negative electrons, because the electrons in the metals are free to move. Instead, the positive charges exist in the nucleus, and therefore their mobility or their motion is very hard. It's very hard to move them. Rather, it's very easy to move the electrons instead. Accordingly, when the electrons attracted to the positive plate, once they reach the negative terminal of the battery, the negative terminal repels them, because negative repels negative. Accordingly, they will be accumulated here. So the number of electrons leaving the positive plate will reach the negative plate. Therefore, at the end, the number of positive charges will be equal to the number of negative charges. Let's measure the potential difference across the terminals of this capacitor when we are charging it. Okay, let's move the voltage higher and higher. You can notice here that the voltage measured by the voltmeter is increasing too. You can notice also that as the quantity of charge increases, the voltage increases, and this is embedded in the equation, in this equation, Q equals CV. Okay, Q equals CV. Q is directly proportional to V. Therefore, as Q increases, the voltage across the terminals of the capacitor increases too. And
let us clarify how the capacitor charges across a generator of electromotive force E. Here in this circuit to the left, you can see a DC generator of electromotive force E, that is, its voltage, or the voltage across its terminals, is E volts. For example, E equals 6 volts or 12 volts, any value of volt, but for sure it's a constant value of volt. Connected in series to a resistor of resistance R, and connected in series to a capacitor of capacitance C. So the circuit contains the three components: DC generator, resistor, and capacitor. First of all, you can notice on the two plates of the capacitor, you can notice the green and the red spheres. The green spheres represent the positive charge in the plate of the capacitor, while the red spheres represent the negative electrons or negative charge in the plate of the capacitor. First of all, before the capacitor starts charging, if you count the number of positive charges on each plate alone, you can notice that the same number of positive charges and the same number of negative charges, or the same number of positive and negative charges. Therefore, we can say that at the very beginning, the capacitor is a neutral. That is, each plate has no excess of charge. Therefore, each plate is neutral. So in the circuit we have a DC generator connected in series to a resistor connected in series to a neutral capacitor. Neutral capacitor means that the capacitor is uncharged. There is no excess charge on the plate of the capacitor, on each plate of the capacitor. The graph to the right will show you after a while the variation of the quantity of charge Q on the positive terminal, on the positive plate of the capacitor, as a function of time. Let's start the simulation. You can notice that the positive terminal of the battery attracts electrons from the upper plate, and then the negative terminal of the battery repels them and accumulates them on the lower plate. So as time increases, the upper plate loses electrons while the lower plate gains electrons, and the upper plate therefore becomes positively charged while the lower plate becomes negatively charged. If you observe the graph, you can notice that as time increases, the quantity of charge increases. The quantity of charge on the positive plate increases, and for sure the quantity of charge on the negative plate increases too, but in the negative sign. You can recognize here that this graph corresponds to the charge in the upper plate and not in the lower plate. That is, in the positive plate, not in the lower plate. You can also notice that as time increases, the speed of the charges in the wires decreases. Therefore, the graph to the right, becomes slower, and the slope of the graph becomes lower and lower as time increases. So I will repeat. Okay. Once the circuit begins to work, the electrons are ejected from the positive terminal or the positive plate or the upper plate, attracted by the generator and repelled by the negative terminal of the generator to the lower plate. Therefore, the upper plate becomes positively charged and the lower plate becomes negatively charged. And this process is called the charging of the capacitor. By the way, in this animation, you notice, or we are showing you, the motion of the electrons in the circuit, not the conventional current. If you remember in grade 10, if you remember, the real current in the circuit is the flow of electrons. But for historical reasons, we assume that a positive current in the opposite direction to this one showing you in this diagram or in this circuit moves from positive to negative terminal. This is called the conventional current. But I will repeat, the current you are watching in this diagram, which is the motion of the red charges or the red negative charges, is the real current and not the conventional current, which is the current of flowing negative charges, and not the current of positive or flowing positive charges. Anyway, this is not very important concerning the positive or negative charges who is moving, but what is important in the case of understanding the charging of capacitor, what's important for you is as follows: that you have to know, as time increases, the upper plate loses electrons and become positively charged. So an excess positive charge will appear in the upper plate, and we can say that the upper plate becomes positively charged and the lower plate will acquire electrons. So the lower plate has excess electrons, therefore it possesses negative charges, and its sign will be negative. And in this case, I say that the capacitor is charged. Concerning the voltage of the capacitor, when the capacitor reaches the state of complete charge, this means that the voltage across the terminals of the capacitor is exactly equal to the voltage across the terminals of the battery. That is, suppose that capital E, which is the electromotive force of the battery, is 12 volts, for example. Therefore, when the capacitor is fully charged, you have to know that the voltage across the terminals of the capacitor is 12 volts too. That is, at the end of charging process, the voltage across the terminals of the capacitor becomes equal to the electromotive force E of the generator. And I will give you another information that when the voltage of the capacitor reaches its maximum value in charging process, therefore the current in the circuit stops. And you can notice this information yourself when you observe that the speed of the last electron in the circuit is very slow. Therefore, when the capacitor is fully charged, the current stops in the circuit.
Increases too, and the constant of proportionality is C. Okay, let's speak about the charging and discharging of the capacitor.
Capacitor charging and discharging. Have you ever tried to reason out how to regulate the speed of a ceiling fan, how to tune the radio sets, how to stabilize voltage and power flow in electric power transmission systems? The answer to all the above questions is capacitor. A capacitor is a passive device that stores energy in its electric field and returns energy to the circuit whenever required. A capacitor consists of two conducting plates separated by an insulating material or dielectric. In order to better understand working of capacitor, we have an experimental setup. In this experimental setup, we can see how charging and discharging processes will perform in the capacitor. When the capacitor is connected to a circuit with supply voltage source, two processes, which are called charging and discharging the capacitor, will happen in specific conditions. Let's first understand the charging process. When we connect the key K in a position A, the capacitor is connected to the power supply and current flows through the In this experimental setup, we can see how charging and discharging processes will perform in the capacitor. When the capacitor is connected to a circuit with supply voltage source, two processes, which are called charging and discharging the capacitor, will happen in specific conditions. Let's first understand the charging process. When we connect the key K in a position A, the capacitor is connected to the power supply and current flows through the circuit. Both the plates of the capacitor get the equal and opposite charges, that is, plus Q and minus Q, and the potential difference Vc starts increasing while the capacitor is charging. Once the voltage at the terminals of the capacitor Vc is equal to the supply voltage, that is, V is equal to Vc, the capacitor is fully charged and the current stops flowing through the circuit. This completes the charging phase. Now let's understand discharging. In the next step, when we will replace the key K from position A to position B, the capacitor will start discharging. When key K connects to position B, bulb will glow with high intensity. Intensity of the bulb and voltage between the capacitor's plates drops down gradually to 0, which completes the discharging phase.
Here is an experiment about charging and discharging capacitor. This is the power supply or the DC voltage source. This is a switch, a single pole double throw switch. It will be when this switch is set in this port, charging will take place, and when we put it in this port, discharging will take place. Here's the capacitor, and here is the resistor, and here we have a digital voltmeter or a program in the laptop that displays the voltage across the terminals of the capacitor in the charging and in the discharging process. Okay, you can notice here, once we start charging, the voltage of the capacitor increases from 0 up to a certain maximum value, and this maximum value, this is the maximum value reached. This is the same as the potential difference or the voltage of the source. Once we start discharging, at the very same instant, the voltage of the capacitor starts to decrease until reaching approximately 0 after a certain interval of time. And you can notice that approximately at this instant the capacitor is fully discharged and the voltage across the terminals of the capacitor is 0. So this is the charging phase, and this is the discharging phase of the capacitor for sure. Let's speak something about the electric energy stored in a capacitor. Okay, suppose we have a DC generator connected to a capacitor of capacitance C. Suppose that at the very beginning this capacitance is uncharged, this capacitor is uncharged. Once we close the switch, an electric current will move from the positive terminal of the capacitor. Okay, we have a capacitor of capacitance C connected to a DC generator. A current will pass in the circuit, and finally a certain quantity of charge will be accumulated on the positive plate here, and an equal amount of negative charge will accumulate on the second plate. The quantity of charge, as I have said at the very beginning of the chapter, Q equals C times P. Okay, if we are interested in the energy stored, electric energy stored in the capacitor, we have to use this formula, E equal half C V squared. In SI units, this is in joules, C in farad, and V in volts. By the way, if we use this formula, we can derive another equation for E. For example, E equal half C. Instead of using C, we have to substitute instead of C Q over V. Therefore, it's half Q over V times V squared. If you cancel this one with this one, you get E equals half Q V. This is another equation we can use to determine the amount of energy. So this is the first equation, this is the second equation, and we can derive another one. I have to start from here. For example, E equal half QV but instead of V I have to substitute Q over C, so it's half Q times Q over C. Accordingly, E equal half Q squared over C, and this is another equation we can use to determine the electric energy stored in the capacitor. Concerning the equivalent capacitance of a capacitor, we have two cases. Case 1, parallel connection, and case 2, series connection. In parallel connection, we have, for example, a DC generator connected in parallel to a capacitor of capacitance C1, also connected in parallel to a capacitor of capacitance C2, also connected to a capacitor of capacitance C3, etc., etc. You can notice here that the main current I is subdivided into current I1 crossing C1, current I2 crossing C2, and current I3 traversing C3. According to junction rule, we studied in grade 10, I equivalent or I total equals I1 plus I2 plus I3, etc., etc. But I, it's Q over T, as you have studied in chapter in grade 10. I1 is the quantity of the electric current crossing C1. It's Q1 over the same amount of time plus Q2 over the same amount of time plus Q3 over the very same amount of time, etc., etc. So Q equivalent equals Q1 plus Q2 plus Q3, etc. Because you can take 1 over T as a common factor here and cancel 1 over T with 1 over T from the left hand side and the right hand side. But remember that Q equals CV, so Q equivalent equals C equivalent times V equivalent equals C1 V1 plus C2 V2 plus C3 V3, etc., etc. But you have to remember in parallel connection that V equivalent equals V1 equal V2 equal V3, so these guys cancels with each other, and we get the final result C equivalent equals C1 plus C2 plus C3 plus etc., etc. And this is the equation we use to calculate the C equivalent or the equivalent capacitance in parallel connection. You can recognize here that this is similar to R equivalent equal R1 plus R2 plus R3 plus etc. in series connection of resistors. So the parallel connection of capacitors is similar to the series connection of resistors, and vice versa. The series connection of capacitors is similar to the parallel connection of resistors. I'm not going to derive it in this video, but I have to say that if I have a set of capacitors connected in series, so this is C1 of capacitor C1 of capacitance C1 connected in series to a capacitor C2 connected in series to another capacitor C3, etc., etc. If all these guys are connected to a generator, a voltage V, DC generator, therefore this generator will assume that all these guys behave as an equivalent capacitance C equivalent in such a way that 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3 plus etc., etc. And this is similar to the parallel connection of resistors. A special case, we can say it in case of series connection if we have two capacitors, C1 and C2 only. In this case, we can say that C equivalent equal C1 times C2 divided by C1 plus C2. This is a special case only if we have two capacitors. It will not work if we have three capacitors or more. Of course, you can prove it. If you can prove it from this equation. You can start 1 over C equivalent equal 1 over C1 plus 1 over C2 and you can proceed in mathematics to do it.